Today, we will discuss network applications and how they operate within the application layer of computer networks. The application layer is the topmost layer in the TCP/IP model, where user-facing applications interact with network services. This layer enables communication between different devices over the Internet. The World Wide Web is one of the most widely used applications, relying on the HTTP protocol to retrieve web pages from servers. Email services, such as Gmail and Outlook, use protocols like SMTP for sending messages and IMAP or POP3 for receiving them. Social networking platforms, including Facebook, Twitter, and TikTok, allow users to communicate and share content in real time. Peer-to-peer file sharing applications like BitTorrent and Emule enable users to transfer files directly without a central server. Video streaming services such as Netflix, YouTube, and Hulu allow users to watch media online by using specialized streaming protocols. Video conferencing tools, including Skype and Microsoft Teams, provide real-time video and voice communication. When creating a network application, developers write programs that run on different end systems and communicate over a network. A typical example is web server software interacting with browser software. These applications do not run on network core devices, as such devices are designed to forward data rather than execute user applications. By focusing on end systems, developers can rapidly create and deploy applications without modifying the underlying network infrastructure. This flexibility allows new applications to spread quickly and be used globally without requiring changes to the core of the Internet. Network applications follow two main architectures: client-server and peer-to-peer. In the client-server model, devices function either as clients or servers. Clients send requests for data or services, while servers respond by providing the requested information. These roles are distinct, with servers typically being more powerful and handling multiple client requests simultaneously. In contrast, peer-to-peer architecture allows devices to act as both clients and servers. Each peer can request and provide resources, enabling a more decentralized and scalable system. This model is commonly used for file sharing and distributed applications. In the client-server architecture, the server is an always-on host that responds to client requests. It has a permanent IP address and is often located in data centers to handle large-scale demands efficiently. The server does not initiate communication but waits for clients to request services. Clients, on the other hand, connect to the server when needed, issuing requests for data or resources. They may have dynamic IP addresses and can be intermittently connected. Unlike peer-to-peer systems, clients do not communicate directly with each other, relying on the server to manage all interactions and data exchanges. The peer-to-peer architecture does not rely on an always-on server. Instead, end systems, known as peers, communicate directly with each other. Peers request and provide services to one another, allowing for self-scalability, as each new peer brings additional resources to the network. Unlike client-server models, peers are intermittently connected and may frequently change IP addresses. This decentralized structure increases flexibility, but also introduces complexity in management. Peer-to-peer networks are commonly used for applications like BitTorrent, where files are shared across multiple users, and Skype, which initially utilized peer-to-peer communication for voice calls. A network application consists of several key elements. The host is the user's device, such as a laptop, smartphone, or desktop, which runs the application. A process is a software program running on a host, and multiple processes can operate simultaneously on the same device. Communication between processes is known as inter-process communication. When processes reside on the same host, they exchange data locally. However, when they are on different hosts, they require a network to communicate, enabling remote process interaction. This communication is fundamental to network applications, allowing data sharing and coordination across devices. Communication between remote processes relies on two key components: process addressing and data exchange protocols. Process addressing identifies the host and the specific process running on it, ensuring messages reach the correct destination. The data exchange protocol defines how communication occurs. It specifies the types of messages exchanged, such as requests and responses, as well as the message syntax, which includes fields and delimiters. Message semantics determine the meaning of these fields, while rules dictate how and when messages should be sent and received. Understanding these principles is essential for designing efficient network applications. Application processes exchange messages using services provided by lower network layers. This communication occurs through service access points, which act as interfaces between layers. Each process is associated with a service access point at the transport layer, allowing it to send and receive data efficiently. The application layer, controlled by software, interacts with transport layer protocols like TCP and UDP, which are managed by the operating system. Through this structure, protocols such as HTTP, SMTP, and DNS can function seamlessly, ensuring that network applications operate reliably over different networks. To identify the Chrome browser running on a smartphone, two key addresses are used. The host address, which is a unique 32-bit IP address, identifies the device within a network. This ensures that data is sent to the correct smartphone. Additionally, each running process on the device is associated with a specific service access point, which is identified by a port number. This allows multiple applications to communicate simultaneously on the same device while ensuring that incoming data reaches the correct application. Together, the IP address and port number enable efficient communication in networked applications. The address of a process running on a host is determined by a combination of an IP address and a port number, forming a socket. This allows network applications to send and receive data through specific communication endpoints. For example, the web server of Politecnico can be accessed at 131.175.187.72 on port 80. Sockets act as communication ports, where a sending process places a message before the network transports it to the recipient's corresponding socket. This mechanism ensures that data is delivered to the correct application process on the receiving device, enabling reliable communication over the Internet. Choosing the right transport protocol depends on the application's requirements. Reliability is crucial for applications like file transfers and remote access, which need complete accuracy. Others, like audio streaming, can tolerate some data loss without major issues. Delay-sensitive applications, such as internet telephony and online gaming, require low latency to ensure real-time interaction. Bandwidth considerations also play a role. Multimedia applications need a minimum transfer speed, while elastic applications, like web browsing, can adjust to varying network conditions. Understanding these factors helps in selecting the appropriate transport protocol for optimal performance. Transport services rely on two primary protocols, TCP and UDP. TCP is a connection-oriented protocol that ensures reliable data transmission. It guarantees no data loss, adjusts transmission speed based on the receiver's capacity, prevents network congestion, and maintains data integrity through error control. This makes TCP suitable for applications like web browsing and file transfers. In contrast, UDP is a connectionless protocol that prioritizes speed over reliability. It does not guarantee data delivery, lacks flow and congestion control, and provides only optional error checking. UDP is commonly used for applications like streaming and online gaming, where low latency is more important than reliability. Different applications use specific transport protocols based on their communication needs. Email, web browsing, and file transfers use TCP, which ensures reliable data delivery. Domain name translation, IP address assignment, and intra-domain routing rely on UDP for faster connectionless communication. Some applications like audio and video telephony typically use UDP to reduce latency, while services like on-demand streaming often prefer TCP for data integrity. Applications such as Skype and streaming platforms use a mix of TCP and UDP depending on the required balance between speed and reliability. Choosing the right transport protocol ensures optimal performance for each application. Different multimedia applications have specific transport service requirements based on bandwidth, latency, and additional needs. Real-time applications like VoAP, video conferencing, interactive gaming, and real-time video require low latency, typically around 200 milliseconds, to ensure smooth communication. Time-critical applications such as telemedicine demand even lower latency, around 50 milliseconds, to maintain accuracy and responsiveness. High-bandwidth applications like HDTV and network-hosted software require large data transfer rates but can tolerate higher latency. Some services, such as file sharing and video on demand, prioritize data integrity over real-time performance, making them suitable for TCP-based transport.